Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. In this webinar, having looked at introduction and overview of SPSS statistics, we're now going to look at a dive into significance tests, what we mean by significance tests, and how they're interpreted and the context around them. They're much abused aspect of statistical analysis, and we really wanted to try and get to the heart of it and explain how to correctly interpret them, how to correctly report them, and how to understand what's actually going on behind the scenes. If you haven't joined any of these sessions before, you should know that these sessions are recorded, so you'll get a link to be able to listen to it back again. This session has quite a lot of slideware in it because there's a lot of conceptual stuff in it we were trying to explain. So slides are going to be important. We'll email out a link to you after the session's ended so you can download those. And if you think it's particularly relevant for colleagues who were unable to attend today, and who may, if you can get enough of them together, we may well be able to arrange a rerun of this on a private basis. The best thing to do is just to ask us. Now, with regard to asking questions, all the lines are muted. We ask you to use the chat panel. My colleague Rachel will be fielding the questions and just checking them as we're going along. We often struggle to fit this all in time, so it's a bit of a rush. So don't be surprised if we don't answer your questions during the chat. We may have to follow up with you offline afterwards, sending emails, which is what we do on a regular basis. But if I can get through it in time, we will definitely check the chat panel and try to answer your questions. If you don't know who we are Smart Vision Europe, and we are an organization, technology company that specialize in statistics, data science, analytics, machine learning, big data technologies, all that sort of stuff. We're a gold accredited partner to IBM, as well as a company called Predictive Solutions and also DataRobot. We work with open source technologies as well. We're a relatively small organization who are veteran employees of the former employees of the analytical software industry. We've all got a deep history in analytical software. I've worked for SPSS since 1995 and IBM and SAS Institute as a consultant and as manager there. So we know a lot about this type of area, and we've a lot of experience of applying it across many different sectors, including the not-for-profit sector and the commercial sector, in hundreds of different applications. So you're in very good company with regard to us talking to you about the context and the correct way to make sense of the world of statistical interpretation when it comes to what are known as significance tests. So our agenda today is we need to start off and address the kind of lance the boil, if you like, of the term significance testing, which is a term that is loathed by a lot of statisticians. And then we need to talk about inferential statistics and how that relates to significance testing. Then we need to talk about p-values or probability values, which significance tests tend to produce. And then we're going to look at three different examples. One example, we look at how to interpret the chi-square test. We're using that because it's commonly used when you're comparing category fields and how they relate to each other. Correlations, we're going to look at that. That's commonly used when we're comparing number fields or continuous fields and how they relate to each other. And then the third one is in confidence intervals. That's commonly used when you're trying to test or see if there's a difference between combinations of category and continuous fields. So that's why we've chosen those three different areas, because they kind of cover the gamut of the different types of data that people tend to have. And the relationships that they tend to test for when they're analyzing. Okay, so first thing we need to do is talk about significance. And this is a troublesome term. It's a troublesome term that was introduced by this guy, Sir Ronald Fisher. And he introduced the phrase test of significance. I'm sure if he had to live his life over again, there are lots of things he would have done differently. And he certainly would have thought very carefully about some of the terminology he came up with, because people tend to take a lot of it quite literally. We know that, when people say things like, but it's significant, it's statistically significant, they they use that as a phrase. You even see politicians using that as a phrase to kind of justify something. It doesn't mean that things are notable when it's statistically significant, it just means that it's past some sort of arbitrary threshold. So in the case of old Ronald Fisher, unfortunately, saying that something is statistically significant is likely to be misunderstood. Significance does not mean notable, does not mean interesting, does not mean important. It sometimes doesn't even mean it's reliable, and even the term test isn't really the ideal term to use. If you wanted to come up with a more accurate phrase to describe it, it would be that significance tests are described as probability of evidence estimates, which isn't, I don't imagine, is going to take off anytime soon. It doesn't exactly trip off the tongue, but literally that's what it is. It is the probability of evidence, and it's an estimate more than a test. Anything else, you do a COVID test, it's closer to an actual test. A significance test is more of a kind of estimate, and it looks at evidence and it focuses on probability. It definitely doesn't say anything about whether or not the phenomena you're looking at and the results you're seeing are important or notable or even necessarily reliable. Okay, so if you're looking at all of the different language around significance tests, the world of significance tests, pretty much comes down to about four people. R.A. Fisher, Ronald Fisher, Carl Pearson, Carl Pearson's son, believe it or not, Egon Pearson, and Egon Pearson's colleague, who he worked closely with, Jerzy Neyman. So if you've ever been through Statistics 101 or Introduction to Statistics course at university, and you've been taught about confidence intervals and null hypothesis and chi-square and z-tests and f-tests and ANOVA and rejecting or accepting and alpha levels and confidence intervals and probability distributions and all that sort of stuff. These are the guys that are responsible for that. And they didn't necessarily get on. They didn't necessarily agree with one another. And in many ways, the paradigm of statistics that they've cobbled together or have been responsible for is a kind of a fudge. It's a kind of a smorgasbord. It's not what statisticians like to say, it's not an exact science. Okay. This approach, this world, this paradigm of statistics is actually referred to as the frequentist tradition. So these are the stats that people most commonly taught in university, p-values and that sort of stuff. That's called the frequentist tradition. And the other type of tradition we're going to be talking about later on, actually. We talk about Bayesian analysis, and that's the next webinar I'm going to be talking about. But suffice to say, we need to talk about inferential statistics before we can get to significance tests. So inferential statistics simply refer to the fact that we're trying to make an inference from something. A statistic or a state, as the term it originates from, is a characteristic of a sample. A characteristic of a population is called a parameter. Now, we can't usually grab data about an entire population. Populations are dynamic, they're changing all the time. Even if we're talking about, I don't know, men aged over 45 who live in the UK, that number is changing rapidly, of course, because people are becoming 45 and older, and people are dying. So this idea that you might want to estimate, say, their blood pressure or something like that, that's a parameter, and you're never really going to get all the data for all the men on that age group in that region in a single location at once for you to actually calculate that parameter. So what you use is a sample. You might be a big sample, might be like 10,000, might be 100,000, might be 100, but a statistic is calculated from a sample in order to estimate the parameter, what's really happening in the population. So that's important because the inference is an attempt to try to cross the chasm, the unknowable chasm between the sample to the population. Okay, so in many ways, statistics kind of assumes that the population is always unknowable. Even if you're saying that the population is everybody in my organization and I have all information about people in my organization, technically speaking, then you don't need to do statistical or inferential statistics because you've got all the data. But if you're talking about all the possible people that be in your organization, or given that people are leaving and joining, then you're back into the world of that being a theoretical population. So what can we infer, how can we infer a parameter value from a population, about a population from a sample statistic? Well, that's made especially difficult, of course, when different samples from the same population are going to produce different statistics. If we wanted to calculate, for example, the water temperature of the Indian Ocean, and we're trying to calculate it to like 10 decimal places or something like that, or the salinity value, you may find that, where you take a sample makes a difference, and the sample size makes a difference, and you're never going to get exactly the same value each time. So in the same sense, if you're just trying to calculate the mean ages or estimate the mean ages of men and women in a population or two groups of people, you may find that as you draw a sample, uh, and time and again, that the values differ slightly from one group to the next, from one sample to the next. And one sample might be 34 for men and 32 for women, and the next one might be 33 for men and 30 for women, or another sample might be reversed, might be the average age for women is 32 and the average age of men is 31. They vary from one another. And in many ways, statistics is the science of variation. That's what it is. It's the best way to describe it. It is trying to account for variation, the fact that things vary. And you're trying to work out whether or not that variation is random, or whether or not you can account for it in some way, whether or not there's some sort of element or aspect to it which is non-random. So is it possible when we're calculating these mean ages in this theoretical world where we have the luxury of taking repeated samples and we're trying to estimate the mean age of men and women, is it actually possible that the mean ages are in fact the same, and that the differences that we're seeing are just a result of the fact that we can't have the true parameter values. We can't look inside the population. We can only rely on a subsample of it. Would they differ from one to the next? Well, to do that, we need to calculate a significance test. Okay, so a significance test, as we said before, does not necessarily mean that it's noteworthy. Instead, these tests, as we call them, simply indicate that the evidence does not support the assumption. There's no difference between certain groups in the population. So here we're asking the question, is it possible that the mean ages are actually the same in the population? And we're going to calculate a number, and that number is going to give us some sort of indication that'll tell us whether or not the evidence supports that assumption. Okay. Now the problem is that in tools like SPSS and other tools, this number is labeled in many different ways. So sometimes it's labeled SIG, and sometimes labeled P, and sometimes labeled prob, and sometimes it's labeled asymptotic significance. It doesn't matter how it's labeled, it's interpreted exactly the same way. So don't get tripped up by that. It may be labeled slightly differently, but it's interpreted in exactly the same way. And furthermore, that the numbers themselves can be converted into percentages pretty easily, because the probability of 0.172 equates to 17.2%. You'll often get a value where it says the prob or the p-value is just 0.0000. These days, SPSS simply labels, I think, the p-values as less, if they're that small, it just says they're less than 0.001. But if it says 0.00, it doesn't mean that there's 0% chance. It just means that, it doesn't have enough decimal places to display how small it is. And you might even get something where it says 0.34. That means 3.4%, or 3% if you're rounding down. So you can always take these probability values and convert them into percentages, and these percentages are the percentage probability, the percentage chance. You just get used to interpreting 0.05 is 5%, 0.1 is 10%, 0.2 is 20%, 0.001 is 0.1%. You just get used to thinking it in those terms. Okay, but what do the percentages actually relate to? Well, we'll come to that in a moment. First of all, if we assume there is no difference or no relationship, very often you'll see people describe tests as tests of relationships between groups or between factors. But when they talk about relationships, what they really mean often is differences. It is whether or not there's a difference, and the difference is the relationship, if you like. So you might, for example, pull out a sample and do a statistical test. In this case, if you were comparing two means, and you were testing what's called the null hypothesis, which we'll come to later on, the null hypothesis being that the means are in fact exactly the same in the population, and you got a p-value of 0.011, it's saying that basically you'd see a difference as big as this, a difference of 2 years between 34 and 32 up here. You'd see a difference as big as this about 11% of the time. Whereas here we've got a difference of 3 years, and it might be a p-value of 0.04, and it's saying you would see a difference as big as this about 4% of the time, and here there's only a difference of 1 year, and it says we would see a difference as big as this about 33% of the time. So, if these are quite small sample sizes, you might well get different p-values as you're coming out of them, or if the samples are very different from one another due to some sort of bias in the data. So that's how a t-test p-values would be interpreted. But again, we haven't really said anything about what we do with these p-values. When we're walking up to that, and we approach that by talking about hypothesis testing. If you're investigating whether or not there's a difference between groups, might be 2 groups, might be 3 groups, or whether there's a relationship such as a correlation between 2 factors with statistics. You're doing that because you're curious to see if there's a difference or a pattern. That means that there is at least an implied hypothesis. There's something that you're guessing. Now, you might think that I think there's a difference between the average age of men and women in my population. This is called the alternative hypothesis. It's labeled H1. But in reality, the statistical test that you're running is focusing on the idea that you're to see if your data supports the notion that there is no difference between the average ages of men and women in the population. This is called the null hypothesis, or H0 for short. So p-values are related to a null hypothesis. The idea being that there's no difference, there's no relationship, and it's giving you a value to help you figure out whether or not the evidence supports that notion that there's no difference. That's just how they're oriented. The relevant test then calculates a probability that indicates if the null hypothesis is true, how often would we get a result as extreme as the one we observe? This is the most important bit in it. This is the bit where people most commonly misinterpret hypothesis tests and misinterpret how to make sense of significance tests. If the null hypothesis is true, how often would we get a result as extreme as the one we observe? Bearing in mind that the result might be not that extreme, it might be only a difference of 1 or something like that, or 0.5. Might be a pretty small difference, or pretty weak relationship. So that means we're focused on the null hypothesis, and we're focused on whether or not our evidence supports it. And at that point, we need to say to ourselves, well, how small or how large does this probability value need to be before we decide that the data doesn't provide enough evidence to support a null hypothesis? Should we set it at 0.32? Because that's 32%. Does 32% seem to be a reasonable threshold? But about 0.00001, that's like 1 in 10,000, something like that. Is that too strict? Clearly, we have to have some threshold. We have to draw a line in the sand where we say if it's less than that, we don't think the evidence supports the null hypothesis. And if it's more than that, we don't think there's enough evidence to reject the null hypothesis. So it's pretty arbitrary. And that level, that line in the sand, is called an alpha level. And R.A. Fisher, almost, I'm sure, to his instant regret, suggested 5%, which is P equals 0.05, which is also 1 in 20. So it's 1/20th of a chance. That's what it is. On this basis, if the probability is less than 0.05, we would therefore reject the null hypothesis on the basis that there is insufficient evidence to support it. The alternative hypothesis, H1, is there only for reference. We never accept or reject it. It doesn't really enter the picture. In fact, we never even accept the null hypothesis. It's entirely one-directional. The most we can do is not find enough evidence to support it, and therefore we reject it. Some analysts argue that this is a limitation of classical frequentist statistics. As you'll see in the next webinar, Bayesian analytics has a slightly different approach to this. It doesn't use p-values. Now, a completely alternative approach to this, as I just said, is the Bayesian statistics, where we can compare how much evidence there is for the null hypothesis versus the alternative hypothesis. And for more information, you can check a little video series that I have if you're not going to join the next webinar. Now, contrary to a lot of statistical teaching, the p-value, this probability, does not indicate the probability that the null hypothesis is true. It does not indicate the probability that the data were produced by random chance. What p-values can do is indicate how compatible or incompatible the data are with the null hypothesis. And that might sound like semantics, but it's not. And the reason why it's not is because the probability of x given y is not the same as the probability of y given x. So you might ask yourself, what's the probability of someone having a full driving license in the UK, given that they're aged 17 or over? I mean, in other words, what proportion of people aged 17 or over have a full driving license? Is it like 75%? Is it 80%? Is it 60%? That's the probability. You could turn that into 0.75, 0.8, 0.6, whatever it is. But that's not the same as saying what's the probability of someone being aged 17 or over, given that they have a full driving license. Technically speaking, if you've got a full driving license, you have to be aged 17 or over. There might be some weird exceptions to it, but it's got to be pretty close to a probability of 1 or 100%. So they're not the same thing. The probability of a null hypothesis being true, given the evidence, therefore, is not the same as the probability of getting that evidence, assuming the null hypothesis is true. So when we say assuming the null hypothesis is true, I tend to think it's quite useful to regard it as assuming we live in a universe where the null hypothesis is true. If you want to, figure out whether or not smoking causes cancer, you're doing a probability test and you're saying, well, I'm seeing a really big difference here between non-smokers and smokers with regard to lung cancer rates. Assuming we lived in a universe where we knew for a fact that smoking did not cause cancer, how often would I get a result as extreme as that? It's a bit like saying how often, assuming my coin is fair, and I've tossed it 8 times, I've tossed it 80 times, and it's come up 75 times heads. It can happen, but I mean, how often does it happen? How often would you expect to see that? So the null hypothesis is pretty important in these tests of significance, and I've put this in gold because it is the golden rule. To correctly interpret any significance test, you must know the null hypothesis associated with it. People think that p-values are about finding effects. They're not. They're about accepting or rejecting null hypotheses. So therefore, to know how to interpret a test, you must know what the null hypothesis is associated with it. So for example, in a chi-square test, it is that the 2 category variables are independent of one another in a population. They are not related. That is the null hypothesis. In a t-test or an f-test, it is that the group means are the same in the population, they're the same value, and the differences you're observing are just an effect of random chance. The null hypothesis for Pearson's correlation, the correlation coefficient, is that the correlation value is actually 0 in the population, i.e. that there's no linear relationship. It is not that it's a weak relationship. It isn't that it's not that it's a strong relationship or weak. It's just that it assumes it's 0, that there's no relationship. There are probability tests out there. There are significance tests out there that actually test whether or not groups have equal spread, equal variance, and they're sometimes called tests of tests. So when you do a t-test in SPSS, it'll give you a Levene's test of equality of variance, because that's an assumption for a t-test that if the group sizes are quite small, it assumes that, well, the group sizes should have the same amount of variation in each one. And therefore, a Levene's test is added. And the Levene's test tells you the probability that the groups have the same spread or standard deviation values in the population. Therefore, if the value is less than your alpha level, you reject it. You say there isn't evidence to show that it has equal spread. And therefore, I might not be able to do a t-test, assuming that only really works if you've got really quite small sample sizes. In fact, t-tests are quite robust. The null hypothesis for a KS-Lilliefors test is that's a test that tests whether or not your data is normally distributed. And the null hypothesis is that the variable is normally distributed. So if the value is less than your alpha level, whatever that cutoff point is, if it's too small, you would reject the null hypothesis. You would say there's no evidence to show that this is normally distributed. This data is not normally distributed. So it's a situation where sometimes people want it to be non-significant. So knowing what the null hypothesis is associated with the test is critical to know whether or not you accept or reject. What is it that you're accepting or rejecting? Obviously, you need to know that. Okay, so let's start with our first example. This is crosstabs. So crosstabs are a powerful way to examine the relationship between categories. And the chi-square test is kind of joined at the hip to crosstabs. It is commonly used as an associated statistical test. Here we're looking at the relationship between gender and employment category in our data set. I'm just going to jump out of the data set and recreate this. I'm going to go to Analyze, down to Descriptive Statistics, down to crosstabs. I've done this already, so I'll run it again. There's gender going into the rows and employment category going into the columns. It doesn't matter which one goes in where. Chi-square is not affected by that. It's just I tend to put the one which has, in this case, if it's got a lot of categories, I tend to put the thing which has a lot of categories in the rows, just because it comes out. I might be printing it out on an A4 page, but it makes no difference whatsoever. I run that, I click OK, it produces this output for me. So I've just done it already, so I'm going to hide some of these outputs. So there it is. There's a little table we can see. So that's what that looks like. It's just frequencies. It's saying there were 206 female clerical employees. There were 157 male clerical employees. There are 10 female managers and 74 male managers. Now, obviously, that's quite hard to interpret because the group sizes are different. So what do? Well, what we do is we rerun our crosstab and we say, okay, I forgot to do this. I'll ask for row percentages to continue in OK, because I want to compare males and females, who are the kind of the key group. 95% of females are clerical workers, 60% of males are clerical workers. Now it's easier to compare them because they're based on the percentages of the totals, of the row totals each time. Okay, so that's all well and good. We have the row percentages, so we can compare gender in terms of employment category, but it turns out the crosstabs can also display what are called the expected counts. So I'm going to go back and show you that. What do we mean by that? If I go back here, I'm going to switch off row percentages. I'm going to switch on expected. So it's saying I got 207 females in the clerical group. I only expect to get 166.3. I know you can't have 0.3, but that's how the value works out. I got 157 men in the clerical group, but I actually expected to get 197. What does it mean by expected to get? Well, all it's doing is it's adjusting for the different group sizes. So it's basically saying if we were evenly distributing them, what would that number be if there wasn't a bias towards females being clerical workers and if there wasn't a bias towards men being managers? And the expected count for every cell is simply worked out as that cell's row total multiplied by that cell's column total, 216 times 364, divided by the grand total. And that gives you an expected value here, 165.4. And you can do that for every cell. So it turns out the difference between the observed and the expected value, the bias, if you like, in that cell, in that group, is called a residual. And if you added up all the residuals in a crosstab, you can see that here we got 12 fewer female custodial workers than we got 0. And here we got 12.3 more male custodial workers than we actually got. We actually got 27. If we add all these numbers together, what do we get? They come out as 0 because the minus numbers cancel out the positive numbers. So that's no good. So what statisticians do is they square the residuals. A value of -3 squared is 9. A value of -4 squared is 16. A value of 3 squared, 3 positive, is 9. The value of 4 squared is 16. So they tend to square the residuals to stop that cancelling out effect. And it means that when we add up all the squared residuals, the larger that number is, the less likely it is that the variables are unrelated in the population. In other words, it's like once we add up all our squared residuals, it's an indication of how much each cell differs or each group differs from what we would expect to get, how much it differs away, how much it varies away from the average value. And the Pearson chi-square statistic is calculated from that, which we can then turn into a probability value. Okay. And here's the probability value here. The null hypothesis associated with Pearson chi-square test is that the variables are unrelated. A small probability value of less than 0.05, that's the alpha level that most people work towards it, indicates that our differences as large as the ones observed will only occur quite rarely if we're assuming that there's absolutely no relationship between gender and employment category. And we would therefore say there's not enough evidence to support that null hypothesis, and we would reject it. And I would do that. Thus, I would go here and call up the crosstabs again. I probably wouldn't necessarily have to ask for my expected, but I could put in the residuals there. You see, this is residuals, unstandardized residuals. I'll ask for row percentages as well. And I'll go to statistics and ask for a chi-square test, click continue and OK. You can see the labeling slightly different now. It just says it's less than 0.001, which is pretty small. So it's saying there's less than a 0.1% chance that a difference as large as the ones that we're observing here between men and women in terms of their employment category would occur randomly, and that's not enough evidence to support that null hypothesis. Therefore, we reject the null hypothesis. So if we were reporting this, we'd say the chi-square test indicates that the probability of obtaining a value as extreme as the one observed is less than 0.01, or in this case, even 0.001 if you want to be really correct about it, assuming the variables gender and employment category unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected. Okay, so that's crosstabs and chi-square. What happens if we're looking at continuous variables? So we're looking at the relationship that instead of between two category fields like job cat and gender here, we're looking at, say, the relationship between salary and age, or beginning salary and current salary, or previous experience and beginning salary. We can't do crosstabs for that because they're not category fields, they're real numbers. We tend to use things like correlations and scatter plots. A scatter plot shows a strong relationship here between our fields' current salary and people's beginning salary. And correlation values allow us to summarize these relationships. So, for example, here's a bunch of charts showing correlations between horsepower and vehicle weight, between different aspects of cars. Each one of these dots represents an individual vehicle, an individual record in a data set. And here we can see that there's a strong relationship between vehicle weight and horsepower, because as horsepower increases, vehicle weight seems to increase, and this almost starts to line up in a line, in a quite tight line. That has a correlation value of 0.859. It's Pearson's correlation. This is a looser one. This is more like a cloud of bees, but it's still kind of going upwards. This is a weaker correlation. It's 0.434. And here is a strong correlation, but it's negative in nature, minus 0.701. Okay, so this correlation values have direction to them. They tell you the direction. It says here, the time to accelerate from 0 to 60 increases the less when you have less horsepower. Because look, it takes me 10 seconds to accelerate from 0 to 60. It's quite short time. But that's in vehicles that have quite a lot of horsepower. It takes me 20 seconds to accelerate from 0 to 60. Well, those vehicles tend to have much less horsepower. This is a negative relationship. Now, if you're thinking about what's a strong correlation, what's a weak correlation, correlations run between +1 and -1. They cannot exceed those values. But values round about 0, close to 0, in the middle, they show no relationship at all. So here's the relationship between miles per gallon and mileage. There's no relationship between the fuel efficiency of the vehicle and how long you've owned it, how many miles you've done it. So, of course, it comes out as random. It just looks like a cloud of points. There's no straight line going through here. I threw this last one in here, this minus 0.671, quite a strong negative correlation. Because you just need to bear in mind that correlations can only see straight line relationships. The correlation here cannot see this bendy relationship. It can't see a curvy linear. It only sees linear relationships. So it's basing it on that straight line, which is forcing through it. In fact, we do a webinar specifically on correlations and how they're calculated and the pros and cons of using them and the different forms of correlation and so on. But there's a recording of that if you want to look it up. Okay. So when we ask SPSS to calculate correlations for us and it gives us values, it's showing us strong correlations and weak correlations. Here, most of these are positive correlations, saying the strongest correlation here is between beginning salary and current salary, which was this relationship here. See that? That's that really strong relationship there. That comes out as 0.88. There is a reasonably strong relationship between education level in years and current salary. There's a reasonably strong correlation between education level in years and beginning salary. And the rest are kind of weak. They're kind of close to zero. So how do I get that? Well, I get that by going to analyze, correlate, bivariate, and I'm going to pick up age, education level, current salary, beginning salary, months since hire, correlations, and that sort of stuff. And I'm going to switch on a couple of switches, put a few switches on here, and it gives me these correlation values. If I double click on this, open up pivot tables, just make it easier for you to interpret it by hiding the statistics in there. So you can see them all. There they all are. There's the correlations here between one value and the next. See 0.8. Here's some negative ones, minus 0.281 between the education level and years. We didn't have a year's age in here. Okay. Why are we pointing this out? Well, we're asking ourselves which ones are statistically significant. Okay. So remember, what was the hypothesis associated, the null hypothesis associated with correlation matrix? Well, the null hypothesis for Pearson's correlation matrix is that the correlation value in the population is actually zero, i.e. there's no linear relationship. It's not that it's weak, it's that it's zero. So with that in mind, when we add in our significance values, you shouldn't be surprised to find that there are statistically significant correlations, i.e. less than 0.05, which are very, very weak. Because what it's saying here is that, well, it's probably not zero. I mean, it's minus 0.097. It's very, very weak. It's very close to zero, but it's probably not zero. So what does that mean? Is that statistically significant? Yes, because the probability of getting a result as extreme in inverted commas as minus 0.097 is still only 0.3034, which is 3.4%, assuming there is no relationship between the two variables in the population. Does that mean it's notable or worth reporting? No, it doesn't. Not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there's no relationship there at all. So finding something that's statistically significant doesn't mean it's notable, doesn't mean there's a strong relationship, because the null hypothesis may just be that there's no relationship between them. It's not that there's a strong relationship or a medium strong relationship. It's that there's no relationship between them. So it could mean that you get statistically significant results when there's quite a weak relationship, and that's when statisticians tend to use things like effect size measures, where they say, well, look how strong is the relationship. And in fact, correlations are a measure of effect size. If I go back here and run this again, you'll see that here it's giving me the significance value. Look, that's not a very strong correlation. This is stronger. Let's see if we got any ones which are actually that's non-significant. That one's non-significant. That's greater than 0.05. Correlation value 0.059. Non-significant. This one's close to 0.05, quite close to zero, but still we would not reject the null hypothesis that the month since hire has no linear relationship with current salary, amazingly. And here we have quite a weak one, but it's significant. So you can see how you need to be careful with significance values, because they don't tell you how strong a relationship is. They just tells you whether or not you can have enough evidence to reject the null hypothesis. Okay. What happens when we've looked at category versus category variables. So that is when we use crosstabs, and we used chi-square. Then we looked at combinations of continuous variables, and that leads us to correlations and scatter plots, where you can do scatter plots to graph the relationships. What happens if you've got a category variable and a continuous variable? Well, that usually takes you in the realm of t-tests and ANOVA, which are a bit much to try to cover in the last 20 minutes of this webinar. So kind of a gentle introduction to that is to think in terms of confidence intervals and use something called error bars. Now, confidence intervals takes us back to this business of comparing averages, because that's where the most commonly associated with. Different samples vary from the same population, as we know that. So different samples from the same population tend to vary. If you repeat a survey or a project, you're not going to get exactly the same results. You calculate a statistic and the results vary from one sample to the next. No statistical calculation can tell you what the actual value of a population parameter is, because we can't see the population. It's kind of unknowable. And we don't have the luxury usually of repeating samples over and over again. But it turns out we can estimate a range of values that it is likely to lie within. And one way to do that is by requesting what are called confidence intervals. And confidence intervals can be shown graphically as these little error bars. This is what error bars look like, little TIE fighters on the side. The mean, in this case, they happen to be means. They could be medians or something else, but they tend to be means, averages, is shown in the middle. And the intervals, the upper and lower intervals, the range that the true mean may lie within, is shown by these two bars, the upper and lower intervals of the bar here. You may find that for one group, the bars are further apart than for another group. They don't necessarily have to be the same width apart. Some means you can be more confident with than others. What drives that, we shall see. Okay. Now, it turns out there's a procedure in SPSS called the Explore procedure, and it produces lots of summary measures. I'll show you it here. You go to Analyze, down to, let's see, descriptive statistics, Explore, and dependent means continuous variable. Let's say if I do age here and I compare, say, those who are ethnic minority against those who are non-ethnic minority. I'm just going to switch off some of the plots here because they're going to get a bit annoying. But continuing, okay. Runs that. It hits you up with loads of different statistics. But here it shows me, for example, for the non-ethnic minority, this is what the mean age is, 34.85. This is the lower confidence interval, 33.62. The upper confidence interval, 36.08. And here for the yes group, they tend to be 38. The people who are an ethnic minority tend to be slightly older. And here the mean interval goes from 36.09 to 40.20. Notice that the upper bound here, this group, is just a cat's whisker, just the tiniest amount below the lower bound of this group. So they don't quite overlap, just tiny amount. Technically speaking, they don't overlap. Though it's very, very close to one another. Okay, so this is where we can get confidence intervals. You can also calculate themselves. Notice that we've got this little statistic up here. You may notice it says standard error. If you think that's like a standard deviation, it isn't. Here's the standard deviation, but it is related to it. We'll come to that in a moment. So here it says the mean age for all employees in the sample is 34.74. This is for all employees in the sample, not for when we break it down by whether or not they're ethnic minority or not. And it also provides confidence intervals for us. So this example, the mean age happens to be 34.74. And of course, we don't know what the mean age for employees is in the population that the sample was drawn from, but the confidence intervals indicate that it's likely to be contained in a range like 33.67 to 35.8. And as we know, drawing another sample would result in a slightly different mean value. If we took a different sample, we'd get a slightly different mean value. But all our statistics are likely to vary from one sample to the next, not just the mean. The intervals themselves will vary from one sample to the next. So they too would be different. In other words, we can't get too hung up on the values of the confidence intervals themselves any more than we can fix it on the precise value of the mean. What we can say, however, is that even if the intervals vary from one sample to the next, they are likely to be broad enough that on 95% of occasions, they will contain the population mean, i.e. the parameter. What we should not say is that we are 95% confident that the population parameter is between X and Y. This is a very hard thing for people to get their head around, but basically if you say that, a statistician will wrap you over the knuckles. That's why I've been very careful of my language here to say that the intervals will on 95% occasion contain the population mean. It's in other words, it's the technique that will find the mean. The intervals themselves will vary from sample to sample. There's no scientific basis to the phrase we are 95% confident. It's the procedure in 95% of occasions will capture the population mean. Now, what I used to do at this stage was I used to jump out to Google and type into Google, how to correctly interpret confidence intervals. And the first answer that you would get is confidence intervals show you that you could be 95% confident the population parameter is between X and Y. So it was actually wrong, and I made a little note on it and said, this is incorrect, and posted that to Google, and they've changed it. It no longer says that. It isn't the best definition it's given now. It's a wee bit woolly, but at least it doesn't say this thing which statisticians hate when talking about confidence intervals. We are 95% confident the population parameters between X and Y. It just means that on 95% of occasions, the intervals will capture the mean. What does that look like? Well, let's jump out. I've actually got a data set here. I'm going to open up a data set. And the data set has 3 million records in it. It's got 3 million records in it. And I'm going to run some syntax here, which is going to take a random sample of data from that. Here we go, simulation. And it's going to calculate the confidence intervals. So first of all, it's going to do a little table. Yeah, I'll just run this bit here. I think I can just run that. And it gives me a little table. It says, look, the population of the 3 million people, the sample mean is 3.33. It's nice and easy to guess that. Then what I'm going to do is I'm going to run this syntax that basically takes a random 50 cases and then calculates the confidence intervals for those random 50 cases. Then does the same thing again for the next random 50 cases. And it does it 20 times. And what we should find is that on average, 19 out of 20 times, it correctly calculates means that capture that population mean of 0.333, or sorry, 3.333. So we'll just run it. Let's run it again. There we go. So there's our population parameter here, 3.333. Here's our first confidence interval being calculated for us. Does it capture that value within the intervals? Let's see. Yeah, it's 2.51 to 401. So 333 is within that. What about the next one? It's 2.2. It's very close to 333, but it's still within that bound there. And the next one, that's 4 point, easily capturing it there. The last time I did this, it got it wrong on one occasion out of the 20 times. So it was, exactly what we'd expect. It was 19 out of 20 times. Okay, so there we go there. Number 5, look, the 5th one does not capture the value of 3.33. It's too low. It's beneath it. Will it do it again? Or will the remaining 16 or 15 intervals correctly capture it? Let's see. So we're up to number 7 now. It's going through that. You can see it's grabbing these 3 million cases and taking a random sample from them each time as it's going through them. And each time looks like so far we're up to the 10th example now. It's capturing that value of 3.33, but the intervals are changing from one to the next. So the technique itself is 95% reliable, if you like, at capturing what the true population mean is. Interestingly here, I had to go down to sample sizes of 50 from 3 million. It's not a very large sample size, but it still does a reasonable job of calculating that, capturing that value. But the intervals are reasonably far apart, 2.69 to 4.27. Okay, we're coming up to interval number 14 here. It's 3.67. Okay, it's still within that range. A 3.54, getting close to 3.33, but still within that range. We've got 5 more to go now. There's number 16, 4 more to go. Let's see. It's not the 17th one. Still 3.33 within that range. 18 coming up now. 3.33. Only 2 more to go. Still within that range. So everything except, I think it was number 5, have correctly captured. And if it is the 20th one, does it do it? It does. Okay, so we're done. So literally 19 out of 20 times, i.e. 95% of occasions, it correctly captured the population mean of 3.33, except on the 5th occasion here, it got it wrong. So that almost, it doesn't always happen like that. Sometimes all the time you get 20 out of 20, it'll correctly capture it, and sometimes 18 out of 20, but on average, it's 19 times out of 20, it will correctly capture the population mean. Okay, how does that work? Well, the thing that drives it is what's called the standard error. When calculating confidence intervals for a mean value, there are other types of confidence intervals, but for a mean value, we use the standard error. And there are other types of standard error statistics, standard error of the median, standard error of the difference, standard error of the correlation, but this is a standard error of the mean. And these are useful for when we need to calculate confidence intervals for the statistics. So this is a standard error here of 5.42. Indeed, just as a standard deviation measures the variation within a sample, you may be familiar with the standard deviation. It's the average variation within a sample about the mean. The standard error attempts to measure the variation between samples, how much a mean will vary from one sample to the next. And it's actually calculated based on the standard deviation here divided by the square root of the number of occasions. It's actually quite a simple calculation. It's just the ratio of the in many ways, the ratio of the standard deviation to the sample size. So to calculate 95% confidence intervals, what you do is we take the standard error and you multiply it roughly by 2, or 1.96 to be exact, because that's a so special number in statistics. It relates to the number of standard deviations above and below the mean that capture 95% of the cases, but that's another story. So if I multiply 0.542 by 1.96, I get 1.062. And if I take that away from 34.74, I get a lower confidence interval of 33.678, which here is just curtailed, if you like. It's just chopped off. And I get an upper confidence interval of 35.802 when I add it to it. And that's how the confidence intervals are calculated. Now, because the standard error is based on two values only, the standard deviation and the sample size, it means that the width, the size of the confidence intervals is affected by, therefore, the size of the sample and the size of the standard deviation. So confidence intervals move further apart when you have small samples because you're dividing the standard deviation by a smaller number, square root of a small number, or when you have a really large standard deviation because you're dividing the standard deviation, which is already a large number, by a sample size, a square root of the sample size. So the confidence intervals move closer together when you've got a large sample in that group and when you don't have a lot of spread in the data, standard deviation. So that means that I can actually graph this using what are called error bars. Here's the error bars here. This is the difference between men and women in age, male and female here. You can see they kind of overlap with one another. And you can see that the female confidence intervals are a little bit further apart here than the male confidence intervals. Why is that? It can only mean one of two things. It can mean either the female sample size is smaller, and therefore confidence intervals are not as reliable, or the female sample size, the female sample has more standard deviation, a larger standard deviation, and more spread within the data. And for the male sample size, it's either larger or they have less variance in them. They have less standard deviation, smaller standard deviation. So if I wanted to just show you how you do that very quickly, no, I think this is closed on me because I've run it against 3 million cases and left it hanging. Let me just kill it. Task manager. I'll just start it up again. Let's see. In that task, we'll just start it again, and I'll just show you how you can get error bars and how you can illustrate these to start that. It will ask me, it will detect that it was shut down and ask me whether or not I want to recover the data and stuff like that. Let's see if this boots up. Oh, sorry, folks, I've pressed the wrong button. I've pressed modeler. Looks very similar. The icon looks very similar to statistics. Let's start statistics. Ignore IBM SPSS modeler, which is another tool entirely. Okay, so saying, do you want to recover your data? I say, no, I don't care about that. Cancel that. Let's go to statistics. Yeah, cancel. Okay, let everything settle down. Hit open. There's employee data here. This is still opening in the background. We can ignore that. Okay, if I want to do error bars, it's here, chart builder. And I'm going to look, I'm going to go to bar. You can see error bars. I'm actually going to use the simple error bar here. You can see this one. So you can say, I'm going to look at mean age. So the continuous variable goes into the vertical axis. I'm going to look at employment category, put that in the x-axis. Click OK at that point. Run that chart. Yeah, and you can see there, for example, that clerical and managers, they kind of overlap with one another. That means that they're probably not statistically different from one another, because it means that if I repeated the sample 100 times, it's possible that you could get clerical workers with a lower mean age than managers or vice versa. But for custodial workers, we can see that the error bars much further apart. That's probably because it's a smaller sample size. But custodial workers tend to be older. The mean age is coming out about 51. And we can see the confidence intervals are further apart. And the fact that they don't overlap with clerical and manager means that, there's probably a statistically significant difference here between they tend to be statistically older than clerical workers and older on average than managers. And that's probably true in the population. In fact, you could take this a little bit further. One of the things I like to do, if you've got quite complex relationships, you could actually throw in gender. Now you look at interactions. It's quite a powerful way to view this. See, now we get interactions. Look at that. Custodial workers, there are no female custodial workers. But for clerical workers, if we just look at them in isolation on their own, we can see that the male clerical workers tend to be younger than the female clerical workers. And for managers here, there aren't very many female managers because the error bars are further apart. And as a result of that, they overlap with the male managers. And that indicates that there's no evidence to show that they're statistically younger or older than one another, probably because we don't have a large enough sample there, but also because, of course, they overlap one another. Okay, so contrast the previous example with the employment variable, which we've just done. The confidence intervals do not overlap the other two groups. So further reading that you might want to engage in here is we have a little series called the Eat Your Blog series, which really goes into this in more detail. What's standard about standard deviation, finding normality, why are normal distributions so important? Why do we rarely encounter it in real life? The gateway to inference, the relationship between standard error and confidence intervals, understanding correlation, making sense of significance tests, and even an introduction to something called power analysis. So when we are writing what model we have to follow, alternative or null or both, writing both hypotheses right or wrong, you can absolutely write down both hypotheses. You can say my alternative hypothesis is this, my null hypothesis is that, that's fine. But when it comes to interpreting the test, you either have enough evidence to reject the null hypothesis or you don't. You don't accept the null hypothesis. You don't accept the alternative hypothesis, and you don't reject the null hypothesis. A statistical test is entirely one-dimensional. It either gives you the evidence to reject the null hypothesis or it doesn't. What's the point of having H1 if we're only testing rejected? It's simply there as a reference point. It's simply there. It's a good, it doesn't make any, it's just there as a reference. It's just there for people to say, my alternative hypothesis is this. I think that, there's a difference between left-handed and right-handed people in terms of blood pressure. Therefore, I'm going to run a statistical test. And the statistical test is going to test the null hypothesis that there's no difference between left-handed and right-handed people in terms of their blood pressure, average blood pressure. It's just there's a reference point. So it's never used. Further reading, we also recommend, there's a very good book by David Spiegelhalter, The Art of Statistics. It starts from scratch. And in many ways, it inspired a lot of this, the series of webinars that we have because he does such a good job, and he was one of the leading scientists during the pandemic and explaining pandemic. He's also very into Bayesian statistics, which I'll be talking about next. You should be aware that we do offer consulting services of different sizes, whether it's just 1 day or 2 days, 3 days, or longer engagements. And you should also be aware that you can source your software directly from us. We offer formal classroom training and virtual training, informal bite-sized training, potentially split over time, maybe half-day classes, something like that. We also offer track technical support services around the IBM SPSS product line for people who are customers of Smart Vision, and we generally offer no string attached technical and business advice relating to all things analytics. In the meantime, thanks very much for logging in. We look forward to you logging in again in the near future. As I say, the next session we're going to be looking at, the still places available on it, is looking at introducing Bayesian statistics. Thanks.